So welcome to our program today. So today we have a great pleasure to have Yao-Yu from UIUC to speak. And Yao-Yu, Joshua got his bachelor degree from Tsinghua University, and later got a master degree from Taida. Now he is now a fifth-year graduate PhD student at the UIUC. And he has been working on a lot of different interesting stuff from the particle physics, cosmology. Now recently, he's been very interested in using the machine learning to apply to the data, to looking for black hole, and now working with a bunch of people like Transgamy and Liu Xin and others. And today he will give a talk about his recent research on future extraction on synthetic black hole image with neural network. So let's welcome Yao.
Okay, so thanks Ken for having me. So it's good to give a talk in person after a long time in the US. So just to make sure that everybody's comfortable, so I've been tested negative twice recently, so I'm pretty safe right now. I'm probably one of the safest person right here. Okay, so today I'm going to talk about my recent work. It's called Feature Extraction on Synthetic Black Hole Images. This work has been in collaboration with members at the University of Illinois, mainly with George and Ben, and project advisor is Charles Gandy. And our paper is on archive, so I don't know whether you guys can see the screen. Okay, so yeah. So I haven't been back for a while, so I thought about maybe introduce myself a little bit. My research spans a wide range of machine learning application in astrophysics these days. So some of my research interests are dark matters, strong lensing, supermassive black holes, and recently machine learning. Before I joined UIUC, I got my master at NTU downstairs and NTSU for a bachelor degree. They are all in physics, so I'm not a computer science people, but yeah, I like coding stuff. I've been very fortunate to work with many brilliant professors at UIUC. So on the DEFN side is my official advisory field holder. So I've been working with him on a lot of cosmology stuff, like dark matter substructures in strong gravitational lensing. And some of them are using more traditional cosmological and statistical tools. And some of them have to do with machine learning. And in the center is the professor I work with most of the time these days is Charles Gandy. So our project has been using machine learning for the event horizon telescopes. And on the right-hand side is Xin Liu, which we also collaborate on using machine learning to help estimate black hole mass from AGM light curves. So I'm also a member of the Event Horizon Telescope collaboration starting this year. So should we turn off the slide or?
Yeah, maybe because the video taking is faster. Sorry.
No problem.
No.
Okay, you can turn off.
Yeah, so this black hole looks really big. Let's see whether this goes better. But anyway, so it's okay. So can you guys see the black holes? Okay, yeah. There's a hole right here. So basically, the story begins with last year. I think the collaboration announced that we have the first image of a supermassive black hole at the center of M87. So just to give you guys a little bit idea about how big this black hole is, it's more than 10 to a billion solar mass, and you can actually fit the whole solar system within this black hole. Because of the distance, it's quite far away from us. So basically, the angular diameter of these black holes is 40 micro-arcseconds. And the current fast resolution for HSD or like gamma has the resolution around 0.01 arcsecond, which is roughly still 1,000 times difference with the resolving power to resolve these black holes. So I think that's why when people want to do these type of black hole image observations, they basically need to pick the right wavelength to do it. And in order to fit this wavelength, they figure out that we actually need to have a telescope that has a diameter around the Earth size, which is called the Earth size telescopes. So I think there are many members, right? Some of the members right here that are within these Event Horizon Telescope collaborations. So basically what people do is that they link up some of the existing radio telescope in the world to try to make a new network to build a really big telescopes that could resolve the black hole image. And the basic idea behind it is called Radio Interferometry. So basically, I'm not going to talk about all the details, but the idea is that you have some source that emits light and it comes in terms of a wavefront. So at some antennas, you'll receive a signal first, and at a later time, you'll receive other signal at another antenna. So basically, there's a time difference when you receive a peak of these waveforms. So you can use that and some correlator, and later on use some algorithm to regenerate these black hole image. So coming back to the project I'm working on, so we're sort of interested in estimating the spin of this black hole. So as an astrophysicist, we want to understand what kind of physics can we learn from this black hole. And spin is one of the interesting parameters because it's actually, spin could actually change the space-time geometries around black holes. And also it's one of the famous black hole conjecture that predicts there will be 3 fundamentals to describe the black holes. And the question we have in mind is that, can we solve this, can we try to tackle this problem in data-driven ways? So by what I mean by data-driven way is that we have a lot of these theories. So we have theories. So you can use a theory to generate a bunch of synthetic data or images. And you try to look at these images to see whether there are certain features that could be telling us information about the spin. So fortunately, our group at UIUC has been working on the GRMHC, which is called the IHARM 3D simulations, which simulate the 3D structure of the black holes, and radiative transfer code called IPOL, GRRT, so that we could map the 3D structure of the black hole into a 2D black hole image. So on the left-hand side is the 4 resolutions of our synthetic M87 images. And on the right-hand side is the same image that conform with the Gaussian blur that make it to represent the current resolving power of the EHC in our synthetic data sets. So basically, we have a bunch of these synthetic black hole movies that could represent for real M87s. So we have different underlying parameters of our interest. So the question is that, can you just directly take a snapshot of one of these images and tell me what the spin value of these black hole is? And we quickly found that it's actually not an easy task because the black hole is evolving. So basically, the in-class variation for certain spin values could be actually quite huge. And so the in-class variation is actually much more scattering than the variation across different classes. So basically, it's if you ask me to directly pick one of the image and guess what the spin value is, I will have a very difficult time to guess it correctly. And to make the problem even more, to make it even worse, there are some possible degeneracies in the spin value. So for example, like these 2 black holes in our simulation, they actually have very different spin value. But as you can see, at a certain time during the evolution, they look very similar. And to make it even worse, when you blur it with the current resolution, they look almost exactly the same. So traditionally in astrophysics, if you are doing a chi-square fitting, like you subtract your synthetic image with the real data, then this method of measuring spin probably wouldn't work because there are multiple degeneracies right here. Then the question we have in mind is that, since this is a really difficult problem, can machine learning help? Because machine learning has been proved to be really efficient in terms of a lot of tasks recent years. So let me go back to a broad idea about what machine learning is. So basically there's something called a bigger framework called artificial intelligence, which as long as you have an algorithm that can do your task, that's called AI. So for example, like there was IBM has something called the Deep Blue that can play chess, but they are actually pretty hard coded, but they can beat the world champion Gary Kasparov at the time. That's in some sense artificial intelligence. And machine learning is a subfield of artificial intelligence, which in this case, learning is the key. So you basically need to have a bunch of data to let your algorithm learn. For example, like one of the famous examples is that we have our spam folder in our email these days. And you don't directly tell the algorithm like which one is spam. They just automatically learn from some of the previous experience on some of the label data to classify whether future email will be a spam or not. And deep learning is one of the subfields in machine learning that has to do with using something we call deep neural network these days. So basically, when you heard of deep learning, basically there's a deep neural network behind it. So with the framework of deep learning, now the question we can ask is that, given enough of these kind of black hole images and their label, by label I mean the spin value, can we estimate the parameter of interest using a neural network? So in a neural network, which people know is that neural network has been famously good at classification tasks. So for example, like you can have cats and dog images that the neural network can recognize whether this is a cat or dogs. And in our case, there's some natural classification tasks called the Normalizing model, which have to do with the magnetic fields around the black holes. But due to the time, I'm not going to talk about that. But the neural network are actually much more powerful if you can use it to do a regression in our case of interest. So by saying regression is that your neural network actually directly outputs the value of your interest instead of estimating them in the certain bin of your class. So in our case, since bin is something we define as -1 to 1, it's actually a continuous range of value. So in our case, we change the last layer of a neural network to do a regression task when dealing with spin. And so the project I'm working on has to do with like you throw in an image and you basically predict the spin as your last layer. And in our case, we pick a famous neural network called ResNet-18. It's one of the convolutional neural network that has been working pretty well in a lot of computer vision tasks. And in our loss function, which we use a mean square loss in terms of estimating lots of parameters. But in this talk, I'm going to focus on spin only. In our training set, we actually include both Normalizing models. And since these are a data-driven approach, so large data is needed to train our neural network. So basically generate 100,000 of these simulated images to train a neural network and validate it on another 100,000 of images to deal with neural networks. So after the training, one thing really important is to test how well the neural network performs. So right here, we actually built up 3 different blind data sets to test it. So blind data set A has the same setup with our training set. So in our training set, there's actually 5 distinct spin values when we generate these images because of the computational cost. So in principle, if our neural network works really well, and our x-axis is the spin prediction, then in principle, there should be 5 delta functions that you're predicting right here. And in that case, it's not, so our prediction is not very different from the 5 delta function. So in some sense that we think that our neural network is performing really well on blind data set A. So that's really encouraging for us. Then the next question we have is that could it be due to some of the prior that we put in the simulation that it's learning from? So in blinded SFB, we actually changed some of the plasma physics in our testing set to see how well a neural network performed under these circumstances. And as you can see, they're beginning to have much more scattering right here. But in principle, the neural network is still doing a pretty good job of estimating the right spin value. So that's pretty encouraging for us. And the next step we're trying to do is that, to have an optimal case, is that to come up with two different spin values that have never been shown to a neural network and see how well it performs. And to our surprise, not to our surprise, is that something we found that the neural network prediction is actually pretty heavily influenced by its prior of these 5 distinct spin values. But overall, the main value of these prediction distribution is still pretty close to the ground truth of these data we put in right here. So in some sense that we found that the neural network seems to be learning some really generalized features to estimating spin in our neural networks. So Paul, for questions.
So have you tried your neural network on the model produced from other people's simulation?
Yes. So I think we found that it seems to be working fine on some of the other GRMHD simulations, but we haven't tried all of them. So yeah. And we don't have enough of their data yet to present this. But it seems to be working fine across the simulations, as far as I can tell. So the next question we have is that, well, this seems to be working pretty well in our own data set. But what kind of physics can we learn, or how can we see what the neural network actually learns? Right here. So this is a famous cartoon I took from XKCD, which, if you are interested in machine learning, this is something that you'll bump into at some day. Like, basically, a lot of people, they are doing machine learning by basically throwing the data into some complex algorithm, and you have your answers, right? And if it's not working, just tune a hyperparameter, and sometimes it just suddenly works, and we don't know why. As a physicist, that's not very satisfying. So we decided to dig a little bit deeper about what kind of things that the neural network actually learns. So basically, we try to look at something called the feature maps of our neural network, try to learn what kind of physics it learns. So to give you some idea about what feature maps is in the neural network, feature maps is they are intermediate outputs inside the hidden layers of the neural network. So basically, if you're using a convolutional neural network, they are the output of your convolutional after your convolutional layers. And because of the convolution, you usually have to do something with the downsampling. So you'll see that your output image is actually smaller than the input image in this case. And a single input right here can actually induce multiple feature maps if you have multiple convolutional kernels. And in our convolutional neural network, there are usually many convolutional kernels you can apply on the same input image. So which is the case for our ResNet 18. So after the training, we decided to take a slice, like do sort of like a brain surgery on top of our trained neural network to look at what the neural network sees in the hidden layers. So basically for our ResNet 18, there's a 5 network place for us to output these feature maps. So they are called the convolutional one, which you apply the convolutional kernel once and then get an output. And there are 4 basic blocks, which is the fundamental units in our ResNet 18 architectures. So one thing you can see right here is that when you go to the later layer, the resolution starts to become lower because of the downsampling. So it's really hard to see what kind of things that we learned from basic block 3 and basic block 4 because the resolution is just too low. So they're sort of uninterpretable, at least for me. And if you look at the feature maps from convolutional one, you can start seeing that there's some change compared to the input image, but since the convolution only be applied once, the feature maps at that layer is still pretty similar to the input image. But when we look at the feature maps from basic block 1 and basic block 2, we found that we can still recognize the ring-like structures of these black hole image, but we can start to see a lot of new features being generated right here. So we decided to take a look at some of the output of these basic block 1 and basic block 2. And in this talk, I'm going to focus on one of them. So basically, to see what kind of features it learns in this synthetic black hole images, we found that we tried to compare feature maps between our trained ResNet 18 and an untrained ResNet. So, but what I mean by untrained is that these are actually something called the pre-trained ResNet. They have seen cats and dogs images or ImageNet data sets, if you know what I mean. And that means that the neural network are able to naturally pick up all the edges about the daily life object. But you have never seen a black hole before. And by comparing the feature maps of these two, and training ResNets have been trained on synthetic data with a task to estimate spin. So by comparing these two, you can start seeing some of the new features that are different from our trained ResNet and untrained ResNet. So one of the key features we find right here is that there's actually a lot of these spiral arm patterns showing up in the feature maps right here in our so these are actually called the low surface brightness features, or because they're actually pretty dim for us to see. And then we decide to output all the feature maps right here just to show that I'm not really cherry picking on these particular features. So in the green box, I selected some of the plots that contains these spiral arm features right here, and trying to compare with the untrained ResNet 18. So we found that these kind of features are actually pretty important in terms of estimating spin in our data sets. So the reason why we call these low surface brightness features is that when you look at the full resolution of the data in normal scale, you usually see the ring-like structure. But if you plot it in a log scale, you can actually see there's a beautiful accretion structures that are actually pretty thin, but they're physically present right there. And the neural network seems to be telling us that there are some information about spin in those parts. And that's really interesting for us. And at this stage, we don't know whether it's we're not 100% sure whether it's a physical features or not, but some of people are thinking about maybe this has to do with something called a frame dragging effect around the black hole. So we're still working on that. But this is basically a case that shows that the neural network learns interesting features that might be useful.
Sorry, so then your simulation assumes there's no noise?
In this case, there's no noise. Yeah, so I think this is a very good question because, like, in reality, we know that we actually train the neural network on top of these images, but in reality, there are actually some blurring effect and noise. So one naive thing we try to do right here is that we actually train our neural network on the more realistic images right here to see how big this actual scattering would be. And this is a comparison of our spin prediction for noise-free and full resolution data, and the one that is controlled with f of hn equals to 20 microarcseconds. And we add Gaussian noise, so the second noise is 10 right here. So as you can see right here, I think the biggest difference is that there's obviously more scattering right here, which is very intuitive as a prediction. But one really important thing is that the neural networks seem to still be able to pick up some of the information even under these noisy conditions. And for the blinded set C, we actually found that the predictions start to deviate from its ground truth estimation. But we've done multiple tests, and it seems like under these circumstances, the neural network usually still gets a sign of the spin value correct for these out of distribution data. So this is basically an example of using neural network to get an idea about how much information on there within this circumstance and how will it perform.
So sorry, can I ask what's plot? What was plot here? I mean, the y-axis you say is blind,
Yes.
and what does it mean?
Oh, so blind data set. So in each blind, so these are the histogram. So blind data set A actually contains 40,000 blind images that have never been shown to a neural network. So these are the histogram of your prediction, and we stack them over to make it a histogram. So if you sum over these plots, so these are in log scale, and if you sum over all of them, they should be like the same to your number of your blind images right here. So I think in blind data set A we have 40,000 of them. In blind data set B we have roughly 10,000 of them, and in blind data set C you have roughly 1,000 of these images.
And you plot the log scale there.
Yeah,
So,
right.
so that's different. I mean, kind of different from usually use as probability p-value or likelihood.
Yeah.
Using log scale, that's pretty, misleading.
Yeah.
For
That's
example, the lower left panel, you show that I think the dash line is 0.25 or 0.75, and that's what was that, standard average or standard prior?
Oh, that's an average for this one.
And, okay. So you have a bimodal, kind of bimodal distribution and average to
Yeah,
0.25.
right. And yes, so I think the reason has to do with that is because we have never seen a spin value right here. So it's very naturally to think it's a 0 or 0.5. It's heavily influenced by its prior knowledge. Any other questions?
Yeah. So then with this kind of plot, so when you actually make an observational measurement, how you would define the error bar on those means? So it's actually, so you have to fit the plot.
Yeah. So these are actually point estimations, so they don't output the posterior or the uncertainty individually. But in I think that's something we're working on, that we can actually output the uncertainty directly within a neural network, and you change the loss function to something called the negative log likelihood. So you can have one neuron outputting your spin value, one outputting the spin uncertainties. So that's something we've done, but we're not going to talk about that in our work. And there are many different neural networks are tackling predicting individual uncertainties these days. Like a lot of them have to do with Bayesian neural networks. Right. So I need to speed up a little bit. Yeah. So one obvious thing is that after you train this neural network, people ask you, well, can we directly apply these to our real images? Like, the answer is, so I'm not going to talk about whether yes or no. I'm actually going to raise up some of the challenges. And due to the time, I'm going to focus on one of the challenges right here, which is the image reconstruction algorithm we use. So in principle, some of you may know that when we do this black hole observation, we don't directly just take a picture and have a picture right here. What we actually do is that we have multiple radio antennas, and they do some measurement in something we call the visibility space, if you are familiar with radio interferometry. And you basically, so these are basically subsampling of the real images in the Fourier domain. And you need to come up with some clever reconstruction algorithm to reconstruct the data, the image back from this subsample data. So usually when you do the reconstructed image will look similar to the true image, but they won't be exactly the same. So when we actually tried a different algorithm or try to do the data reconstruction blindly, these are actually the 4 images that are in the collaboration paper from 4 different groups. And I think one of them, some of the members are involved with right here. So as you can see that these 4 images, it depends on the scientific question you're asking. If you're asking whether this is a real black hole, then I personally will call it. But if you're trying to use this to estimate spin, the features right here in these 4 different images could be quite different. So we need to be much more careful about this. And also, like some of these images, in principle, they do carry uncertainties right here. And so how to include some of these uncertainty right here when you make a prediction is actually quite crucial for really answering these scientific questions. But a much more natural way, I personally think, is that like whatever happens in visibility should stay in visibilities. So if you're not familiar with visibilities, this is also a snapshot I took from the collaboration paper. So on the left-hand side is something we call the UV coverage, which is the subsampling of the data from pairs of telescopes. So imagine you have a Fourier transform data, and you're only collecting data from this data point. And on the right-hand side is something we plot out called the visibility amplitudes, which means that when you sample this data, you are sampling a bunch of complex numbers. But when you take the amplitude, if you have a ring-like structure, the Fourier transform of this ring-like structure will form some kind of like Basel functions. And if you square this Basel function, they'll start looking like something like a dipping things right here. So if your data are lying on top of these present model with dipping things, I call it right here, we think it's more likely to be a black hole. So the question for us right here is that these are more like more close to the raw data of your measurement. So can we directly estimate the spin from this kind of data and make a scatter plot, something like that? And the answer, so the task for a neural network is that if you have enough of these mock visibilities, so basically what we do right here is that we can use something called some open source software called DHT imaging to generate a bunch of these mock visibilities from our synthetic images and train a neural network on top of these synthetic visibilities to see how well it can estimate the spin values. And these are something which is called the end-to-end approach in machine learning, which you go to a really raw data and try not to do image reconstruction, but you just directly go from raw data to your parameter of interest. And these are some of the things I've been currently working on. So these are actually measuring your parameter from sparsely sampled Fourier domain data. And it seems to be working fine because for this example, the spin ground trip is 0.5 and the estimated spin value is 0.63. So because of this is a still ongoing project, I'm not going to show the summary statistics, but I think the overall idea is that this seems to be working all right here. And I'm pretty excited about this because I think this tool is actually quite general and that can be applied to any kinds of radio interferometry data, not only for M87, it can be applied to Sagittarius A stars or even other ALMA data if you're interested in protoplanetary disks and you have certain parameters you want. If you have enough data, then this pipeline could potentially serve your task well. And also, a lot of challenges in machine learning is that because things usually train on simulation, so when you apply on real data, sometimes they wouldn't work. But I think this pipeline could possibly actually work on real data because of the sparsity. due to the time, I'm not going to talk about why I think so. But I also want to shout out to some of my collaborators, Katie Bauman and Hassan, on another paper they've been working on. So some of the ideas are already right here. So the reason why we think this pipeline could work is that we actually thought that radio interferometry is actually pretty similar to something we call the autoencoders in machine learning. So autoencoders that you have is a type of neural network that you have some input image, you pass it through a bunch of neural network, and there's a decoder, and you basically do the reconstructed images. And it's kind of like unsupervised learning ways of doing things. But I'm not going to talk about machine learning. But the idea is that I found this really interesting because I found there's a lot of similarities between these two. So basically, in our black hole observation, you have a real image right there on top of the sky. But due to the budget limit or real constraint, you actually have an encoder that is sparsely sampled your data into a representation space, which you'll have less information about it. But when you try to understand what this data is, usually people need to use a decoder, which means in our case it's an image reconstruction algorithm to reconstruct these visibility, which is really hard to directly interpret if you're not an expert in this field, back to a physical space and do the data analysis right there. But sometimes there'll be uncertainty right here when you do the decoding part and encoding part, which is really hard to track. And the reason why I'm excited is that basically our neural network are just directly taking the visibilities and attach another fully connected neural network to directly analyze data in our representation space. So you're not trying to impose additional information from your prior or all things. So this is more, I think this is a really interesting way of looking at radio interferometries. And usually I think this will work is that basically when you build a convolutional neural network, you're actually removing the decoding part and the output part and replace it with a fully connected neural network at the last few layers. So I think this is pretty similar, pretty represent our spirit of a pipeline. Yeah.
Well, so since you're already in the summary, so maybe you.
Okay. Right. So I hope that in this talk I convinced you that the neural network recovers spin from high precision synthetic black hole images, and they also actually can be used as a feature extraction tool. And in this case, they found that some of those super sprites in this region could contain some information about black hole spin. And neural network also provide an end-to-end tool for data analysis, for example, like radio interferometries. And obviously, more future work would be needed if you really want to apply it on real data. So here I'll stop and take questions. And if you are interested in that paper, you can take out a phone and scan the QR code. If that works for you. So thank you.
Thank you very much. Any questions?
Yeah, so usually I'm a little cautionary about the visibility analysis. So the reason is that when you are looking at the model, so basically your black hole is like sitting in a vacuum, right? So you only have black hole in the image. If you look at the actual observation and then look at the visibility, then basically you are looking at the convolution of black hole and many other things surrounding the black hole. So basically all the excited ionized gas. So they are presumably like 2-3 order of magnitude fainter than this very bright ring. But just from your models, it looks like those features are actually those features which are like 2-3 order of magnitude or even fainter than this brightest rings are actually pretty critical when you are trying to determine the spin. Yeah, so this kind of thing. So basically, so this faint feature are as bright as any other ionized gas feature surrounding the black hole. And so if you look at the visibility, they will just get confused. And the advantage of making images, like you are limiting your analysis to this very small area, right? Basically, you try to ignore all the confusion outside of this very small region. So
Right.
that's one of the advantages. But then there's a disadvantage of having this construction error. So there are pros and cons to the approach. So such choices, and you need to figure out a way to avoid being confused by any other extended ionized gas structure around either the M87 black hole. Say if there's a jet, then you will see it. And the Sagittarius A star, there are many other ionized gas structures.
Sure. Yeah, actually, totally agree with you.
But can the network be smart enough to only look at those confined features in the visibility space?
So I think yes, because they are basically trying to find whatever you can maximize your information and find a universal fitting function for it. So if there for a case, if there's more information, for example, like I don't know, maybe at a longer baseline, then eventually you could train a neural network long enough, they'll figure out that's the places where most information are, and they'll start to come up with an approximation of the functions right here. I think one thing that are really interesting that we're currently exploring is that, so far all of these things I show are using the 2017 antenna configuration for M87, but in the future if you have additional telescopes, then you could have more coverage right here, then we could try to use it as a tool to estimate how well it could do under these circumstances. And one thing I would like to mention is that we could also use it to test different noise model, how well you can estimate the uncertainty under different noise models. And it has been quite successful, at least in particle physics experiment. So they try different assumptions and estimate the likelihood of things.
So this was already mentioned in the previous paper, but we already see the time variations.
Yeah.
So then we have the latitude more of the image. That's much nicer to compare.
Yes, so one of the things that our neural network, we found in our neural network that we didn't show right here is that you can have some time series data right here, and if you can build a neural network to basically take into time series data, we actually found that you could constrain spin better. Yeah, that seems to be what we found in our synthetic data sets.
How much better?
Depends on the cases, yeah, and depends on like what do you mean by time? What's the gap of the time evolution and how many data are there? But I think it's better. Yeah.
So big difference. Which is important. If you have that, do you need a different mode of the image, or if you have the very similar image but very different time? I think like even for the different time, the structure is the same. It already contains some kind of information.
I think basically what Charles and I tried is that if you have do observation, at least for M87 within different weeks, like they could improve some of the spin estimation really well. So some other things we also tried is with polarized data, which I'm not talking about right here. Well, there could also be some of things for Sagittarius A stars that if you think of Sagittarius A star, it's actually a movie that you're taking from Radio Interferometry. And the time series part is already encoded in the visibilities. So for the reason I'm excited about this pipeline is that for Sagittarius A star, you don't actually need to build another neural network to do that. That these autoencoder structures, they can take into whatever visibilities right here to do estimation. So I think that's a really interesting and powerful.
Yeah, very nice talk. I'm not an expert, so I was just curious. So the input to the neural network is a sort of 2D image, right?
Yeah.
I was wondering if you could also supplement it with some additional observables or constraints, like I could imagine a temperature.
Yeah, so that's a very yeah, I think that's a very interesting useful suggestions. So some people are, so basically in the previous project, like not for the visibility ones, would basically take an image and output your parameters. But in principle, you could provide other things called the metadata, like what's the condition when you do observation? Is the weather good, or if you know some other constraint from other measurement, you could actually provide that to the last few layers of a neural network and use it as a feature to help you better decide what's your parameters. Yeah, so I think that's something that people have done in other fields.
Dina?
So have you tried other architectures and see whether or not they have better performance?
Yeah, so I tried a lot of them, and I found that ResNet 18 seems to be working fine because they have the skip connections. So basically all the neural network with skip connection outperform the one without it. But I picked ResNet 18 instead of a bigger ResNet because I found the results are sort of saturated right there. So bigger network wouldn't help that much improvement. But training ResNet 18 is probably good enough for our computational cost and estimating the data precisely.
So another thing is you only measure spin. I just wonder when you get the output, it's the spin only the parameter, or actually you also output the mass and other things, and whether or not the algorithm can have a good constraint on other parameters.
Yes, so basically if you can look at the numbers right here. So basically I changed the last layer of the ResNet 18. So if you try the pre-trained model, there's actually 1,000 class. And so there are several parameters of our interest right here. So they include spin and the mass of the black holes, and something called the inclination angle and the accretion rate, and also the position angles. So when we output some of the angles, we actually need to project them into sine and cosine, so they will have a continuous range when they go from 0 to 2 pi. So I think that's sort of like some of the parameters we try to predict right here. But we're still working on that paper, so we have a full coverage of all the other parameter estimation.
So when you do machine learning, you're actually learning all these parameters simultaneously, right? Instead of say just speed, but it fixed mass, fixed financial.
Yeah, so you can, well, in principle you can do two, but I personally like a neural network that can output multiple parameters at once.
Well, I mean, from observation, you only have a single image.
Yeah.
So you have to learn all parameters at the same time.
Yeah, exactly. Yeah.
Any other questions? Disconnect.
So since we didn't see the magic sample data usually yet, but I'm just wondering if you got some simulation on that. The time scale is quite different. So.
I think that's probably I don't know how much I can talk about that.
Oh, I forgot you having a collaboration.
Well, we can talk later. I think the idea is that, well, you can use the similar neural network architecture to do analysis on that. And even if some of the variability is encoded in the visibility, you can still use the same type of neural network to do that.
Good. Any other comments, questions?
Very nice question. So when you mentioned the challenges for using machine learning for determining spin, you mentioned like noise and data reconstruction.
Yeah.
But in one of the slide you show, it seems like you can also use machine learning to do image reconstruction.
Yeah.
Is that true?
Yeah.
Yeah.
So actually, there's another paper that I think it's from a group in Caltech. Like they actually they use something called the normalizing flow. It's a type of neural network to reconstruct the images. I don't have it right here. But the idea is that there are basically killing algorithm and regularized maximum likelihood when people are trying to reconstruct the visibility back to a real image. And basically these algorithms trying to pick the most possible image, but if you really want to track out all the other possible images, and it's slower if you want to do MCMC right here. So people are start exploring using a neural network to output multiple images from same visibilities that carries different probabilities. So I think that's something people try. And they actually also tried on real M87 data. So we have a neural network reconstructed images these days.
So then in principle you can directly get a spin or black hole mass. So you don't have to rely on other methods to do the image reconstruction.
Yes.
So all the way to
yeah, so basically I'm saying that, well, I'm sorry for some people doing image reconstruction, but if you have enough data, then you can directly go from visibility to your parameters of interest if you really trust your training data and the labels. Yeah. If I have a lot of protoplanar disks, and I know what's the ground truth, then the same pipeline could work. You will have interesting scientific questions.
Any other comment, questions? Okay, if not, let's thank Joshua again.